Well, hi everybody. So in this video, we're going to build these two boards. And one of them is the power supply board, the other one is the protection board. And these are much improved over the original ones. So before we get to building the boards, let's look at the schematic a little bit. So this is the schematic of the power supply board, and this is the original one that's in the amp right now, as it is. And if you break it down, there's actually 3 power supplies on this one board and the soft start for the capacitors. The soft start is just a relay that's connected to the negative 88 volt supply, and as this charges the capacitor up and this comes up to a certain voltage, it'll pull the relay in, and the relay will bypass this 3.3 ohm 20 watt resistor. And the resistor is in contact with a thermal fuse, so say something happens that the voltage doesn't go up high enough to bring in the relay, or let's say the relay fails or something, all of the power coming off of the mains going into that big toroid transformer will be going through this 3.3 ohm resistor, and it's going to get very, very hot. And you're also putting some sort of a big load, into something that's shorted out or something like that. So this thermal fuse will open, and it just protects the whole circuit. The whole idea is to protect, as best you can against a component failure. You want to isolate the failure to the one component and not cause other things to burn up. So that's that. Now, if you look at these are just identical power supply circuits, just working in opposite polarities. So this handles the positive power supplies for your plus 32 volts and your plus 68 volts, and then this handles the supply for your minus 32 and minus 68 volts. And that's really all it is. So this first one, to get your plus and minus 68, it's just 2 transistors and a Zener diode is the main part of it. And what happens is this Zener diode here will hold the emitter of this little Q3 resistor to its set Zener voltage, which in this case is, I believe, 32 volts. See how it says 32 there? I'd have to look this one up. And essentially, there's a feedback circuit, and this transistor uses a voltage divider bias off of the output. So it picks off a voltage from that it creates between these resistive dividers and turns on this transistor. This allows feedback so that if something, as it changes, this will change a little bit in its current and so forth. And this current pass transistor will regulate the voltage. That's how that's all done in here in a nutshell. These 2 resistors here, what is that, R1 and R3? This 2.7 Ks resistors. This acts almost like a current source to give you the bias current for Q3. And you can see they have a capacitor here to smooth that out, and also to for any real rapid changes, you know what I mean? I think this will affect that a little bit. Not every circuit has this capacitor in this position, but this one does. So essentially that's all this is, and they just have a reverse, the reverse polarity version of it on here. And then that gives you your 68 volts, and then you go through this 820 ohm 2 watt resistor into a 32.6 volt, or what is this? Yeah, no, I think this is another 32 volt Zener again, and that's what gives you your 32 volt. The problem with using these Zeners in this manner is that they have to handle a lot of current if a lot of current is being demanded by the power supply, by the load. And so what can happen with these is these transistors will tend to run pretty hot. This current pass transistor is directly run, directly biased by this little transistor and this Zener right here. And there's better ways of doing this. So these quite often would run hot, and that's why you'd see a lot of times in a high hours machine, you will see that the circuit board gets discolored, And a lot of times these transistors will drop in gain and so forth because with age, because of the heat. It'll just break them down over years. So it's not uncommon to see problems in this area on all of the amps with this style of linear regulator like this. Now down here is a little bit better design. It's the same idea, but in this one they're using a Darlington transistor, and that kind of spreads the current a little bit. So this will run a little bit cooler. And you can see this is for the 13 volts, and it's coming in off of a separate winding of the transformer, if I remember correctly. And so it doesn't, they have 20.7 volts here, just the unregulated going in, and then it's dropping it down to 13 volts, and this is relatively low current. I think this drives some of the indicator lamps on the front of the panel light lamps, and I think it does control some circuitry in the tuner section. So that's the power supply in a nutshell. Now here's the new and improved one in the new board, and I think I have everything in there. Let's see. Yeah. Up here, just like the 13 volt, here is a really simple one because they're just using an LM217 linear voltage regulator IC. It just looks like a TO220 transistor. It's a 3-terminal device. And same thing, they have a voltage doubler circuit here, it looks like, with the 2 diodes. And it comes in, and then you have your linear regulator chip and a couple of components, and there's your 13 volts coming out. Very simple, and this will be a lot more reliable because there's no transistors or anything to wear out. And these linear regulators are pretty good. They usually last a pretty long time. In the same manner, instead of using these Zener diodes on the output of the 68 volts and relying on this to do all the regulation for the 32 volt, they're using again an LM237 and an LM217 regulator IC instead of that, and these are much more efficient and going to run cooler, and they have a lot more tolerance for higher current than the Zener diode. They're not going to drift. The problem with Zener diode is as you draw more current, they heat up. As they heat up, their voltage changes, and because it's a diode, it suffers from all the same problems as any diode or any transistor will, or any semiconductor device. But these have circuitry inside of them, these little ICs, that compensate for that. So this is going to be really stable for your plus and minus 32. Also, quite a bit of improvement's been made to the plus and minus 68, in that when you remember over here, you had this voltage divider here for your current, that acts kind of like the current source for this transistor. Now they have an actual active current source where they're using 2 transistors, these reference resistors, and these green LEDs that provide a consistent voltage drop as a voltage reference. So this is a constant current source. This is a really common design. You can, lots of books and things online will show this same circuit. It's used in many places. Very typical and reliable. And that provides a constant current source that's not going to drift with changes in voltage up here or anything like that. In addition, they added a second transistor, just like this had with the 13 volt. They're now using a Darlington pair for the pass transistor output. That's going to allow this to run, again, a lot cooler, and they put it on a much bigger heat sink. So instead of that little bent piece of aluminum that they're using now, this is actually on a proper aluminum heat sink with fins up here. You're still using a Zener diode for the reference, but because of the current source and everything, this thing's not going to draw heavy current. It's the way this thing is designed. You still have the feedback and all that. None of that changes. But again, this is a much more stable and reliable power supply. So you can see the improvements that were made. It's doing the same thing. It's just that the voltage that's coming out of this is going to be a little more stable, especially with changes in temperature and load and things like that, than the original one. And you probably won't have to ever, you'll never have to repair this for many, many years. I mean, this design, think about it, lasted 40 years. The problem is amplifiers that were used every day and listened to all the time, these failed. And they didn't take a really long time to fail. This one can take constant use, and I don't think you'll see much trouble with it. So, good design. Now the protection board and the main, power supply, again, is pretty simple on this one. You just have a big unregulated supply. These are the big windings on the toroid transformer, one for the left channel, one for the right channel, and that's giving you positive and negative 76 volts for each channel. So you just have two separate power supplies, split power supplies, with a center tapped reference for your ground, and you have positive and negative 76 here, positive and negative 76 here. This will go to right channel, this to left channel, or vice versa, and not much there. The stud diodes that they're using in the original board are pretty good, and they very rarely, if ever, fail. They're mounted to like a metal bracket, and that bracket actually acts like a small heat sink anyway. And you never really have much trouble in this end of things, other than the big filter caps that go to it out there. They can sometimes get leaky or go high ESR. Over here is a little more interesting. Pioneer really started getting into this integrated circuit for the Protect circuit. This PA 3004, there were different versions of this PA, these protection chips. This is the one that Pioneer uses, and it's essentially all the circuitry for your Protect circuit in an IC. It's a single inline pin package, so it's just an 8-pin chip that kind of sits up on its side. We'll look at it maybe when we pull the old board out. And with minimal components out here, it does your midpoint protection. It does the, for DC offset, it does your overload protection, your voltage sense protection. All of that is done by one chip. So it's really a simple circuit, and all it does is drives this relay here. It also does the delayed turn on, so that you don't hear that thump when you turn the amp on as the power supplies are stabilizing, and the transistors don't come up evenly. That's what gives that big thump in the speaker. This waits for everything to stabilize, and then it pulls this relay in, and this relay connects the amplifier to the speaker terminals. It also disconnects the amplifier from the speaker terminals whenever it senses a problem. And there's really not much you can do with this. If this chip fails, you have to replace the chip, and if you can't find this chip, which is the further out we get, the harder it's going to be to find these, you're going to be out of luck when that happens. So if we look at the schematic for this, you would think it's complicated, but it really isn't. You have the same two big power supplies, and they're unregulated, but this time you have transistors that are each individually on their own little aluminum heat sink. They're fast recovery transistors. They're modern, much better transistors. They should have a lot less switching noise and so forth than the originals. So this is, again, an improvement. And this is the new Protect circuit. Instead of a single relay that drives two sets of contacts, they're just disconnecting, both speaker terminals with one relay. You can see that right here. They went to two individual relays with their coils in series. So these are 24-volt coils. So in series, it would be a 48-volt circuit. And I believe this is a 48-volt coil. So by splitting this up, these are actually, this isn't anatomically correct, because I believe the relay that's used in this is a 2-contact relay, or a double pole relay. So each of those contacts are in parallel with one another. Now that's not as good as a bifurcated contact relay, but it's going to do a similar thing in that because it's a mechanical device with little spring-loaded terminals to hold the contacts, one is always going to make contact before the other. So one terminal or one contact is going to get the arc when it comes in or it goes out, and the other one is going to stay clean because it comes in after the contact has been made. So this should kind of resist quite a bit the tendency for the contacts to get pitted and tarnished like they do on some of the other relays you see. And by having 2 contacts in parallel when they're touching, you can handle a lot more current. So again, an totally improved design. The protect circuit is very simple. You have 1, 2, 3, 4 transistors and some diodes and some resistors. It's very simple, and it does the same thing. So you still have your AC detect, your midpoint detect, your power detect, all that stuff. See, here's your plus 76. Everything is still, all the same signals are being used. It's just instead of doing it with an integrated circuit, it's done with discrete components, and if something fails, you can just replace that one component, which makes it a lot more service friendly. Now these boards are available on eBay. That's where I purchased them. This is not a paid endorsement or anything. I've used this same guy who's making these. This is based out of Canada, and I've used his board for his replacement power supply board for the SX-1280, and that went really well. There was one little design changed because it turns out that I didn't even realize this. There were 2 different versions or revisions of the 1980 power supply board. I can't even remember what it was. I'd have to go look it up. But since then, he has come out with 2 different boards, or a board that's able to accommodate both. I had to make some slight change. I don't remember what it was, but these are definite drop-in replacements. When you get the board, you can get them pre-assembled with all the components. It's going to cost a lot more. But if you're like me, I kind of get a lot of enjoyment and satisfaction out of building the board myself. Not that I think it'll be any better than the one you get pre-built, just because I like doing it. This is a hobby, remember? I'm not doing this to make money, and I'm sure not doing this out of necessity. I'm doing this because I enjoy it. And I have a suspicion that most of you out there that are into this are the same way. So it's cool to get it. They give you a bill of materials list down here. There's a written one in these pages that you can see at the end, see all the things. But they actually saved a shopping cart at Mauser, and you can go on there and just order that shopping cart, and it'll be all the parts you need for this. And they'll be the correct parts. They're very high quality. They're coming from Mauser, so you know that they're certified, genuine parts. And that's the way I would go. Same thing with this one. They also will send you this printout, and you can download it. They also have a place where you can download all of this. I don't remember if they show it somewhere here where you can actually download these documents someplace on here, but let's see what it says. Yeah, right there. So you can see you can actually download the online documents. And they also give you the printed version like this. It really does a good job explaining, what you need, and it kind of talks you through assembling the board, how to, you know, if you make a mistake, how to remove a component. It gives you a few ideas. If you don't have really good desoldering station or something, gives you some ideas. And then how to install the board, which you might think, you know, 2 screws that goes in there, but no, there's a whole bunch of wires that have to go on here, and they're wire wrapped on the original board, so you'll have to cut them off. Luckily, they give you screw terminal blocks for this that'll go in here, so it's just as simple as stripping the wire back, pushing it in the terminal, and tighten it down. So that's not too bad. Okay, I have the soldering iron turned on, and so everybody tells you, you know, work high or low to high, you know, the lowest components on the board first, and then build up, and that is a good practice to do. But honestly, whatever's most comfortable for you, whatever helps you to be successful in doing this and doing a neat job, that's the way to go. And that's how I see it. I don't really have my microphone on, and you probably couldn't hear me. But like I said, you mainly just want to make sure that you do it in a way that you're comfortable. So I'm going to go here. I'm going to open my page. I'm going to get started here with these components. And I'm going to start right up here in the corner with R1, simply because I want to. So R1 is a 1/2 watt, 10 ohm, and it looks like 5% TR. Okay, that's what that looks like to me. So let's go find that, and I'll be right back. Another advantage if you order these parts from the shopping cart that they attach on the instructions is, if you notice on the label there's customer part number, and take a look, R2 and R14. So it makes it really easy to identify the part with the parts list. So you can see there's R2 and R14, and there's all the part numbers, and you can line them up. It just makes it so much easier. Okay, R2. This one right here looks like the right space. And R14 is going to be the same, which is R14 right next to it. And I'll go one more. There we go. Okay. And I flip it around. Okay. And let's see, R14. And R2. There we go. We'll solder those, and we'll be right back. Okay, the resistors are all in, and now I'm going to do the diodes. And that's going to be all these: D1, 4, 9, and 12, 2 and 11, 3 and 10, and so forth. So those are going to be both the actual diodes themselves and the LEDs. We're going to get those all replaced. So the first one I'm going to do, because these ones are out. So let's replace these, or install these, I should say. These ones right here, D3 and D10, those are the two that I want to do right here. So let's see, where is 3 and 10? That's fun in and of itself, looking on this board. So there's D3 and there's D10 right there. So let's see. I'm going to do D3 and D10. I'm going to cheat a little bit on this one. I'm going to solder them from the top. If you get the leads cropped to the proper length and and you have these plated through holes like this, you can actually solder from the top, and gravity will just kind of wick it right down through, as well as the capillary effect. And both sides of the board will be soldered perfectly. You don't have to even flip the board over. That's it. Let's see how it did. So there it is right there. You flip it over and you can see perfect. So that makes it a lot easier if you can do it that way. 1, 4, 9, and 12, that would be these LEDs, or LEDs as some people like to call them. Let's put in our LEDs. Let's use our heads and install the LEDs. 1, 4, 9, and 12. Now these are part of the current source, and this is a very common little circuit that you see for current sources. The unfortunate thing is, if you look at this where you put the diodes, like there's D12, you can see how there's a flat spot. Most of these will have a flat spot and then a rounded spot, but if you look at these diodes, they do not have that. So you're going to have to go by, you can either go by the length of the lead, and usually the length of the lead is going to be, here, I'll draw this out. A picture's worth 1,000 words. So let's back this up a little bit. So most of these LEDs or LEDs will be kind of like this, and then they'll have a flat spot, just like that. And there'll be a lead that comes out this end and one out this end, so kind of like if it's domed like this, this will be the little flat spot here, and it'll be one lead here, one lead here, and essentially one lead will be longer than the other, and the flat side is always going to be your cathode, and the rounded side will be your anode. And with the actual lead length, if you look at this, the longer lead, again, is the anode, and this is the cathode. And which your plus and minus, you can say. And the way to tell if that's set up correctly or not, because sometimes they get it backwards. I've had some of these that come from China and so forth, where the lead is actually the cathode, the long lead, and they get it wrong. But anyway, if you look inside here, I don't know how close I can get, but take a good look at that. Pause the video if you have to. But if you look, the long lead is going to have like this little part that kind of looks like this, like a little flag. And then the other side is going to have what I call the anvil. And a lot of people call it the anvil, just like that. It's the larger element of the two. Okay, anvil. Okay. And the anvil is your cathode. So if you're wondering, which side's the anode and the cathode, that's the anvil. The anvil is supposed to be the flat spot. So if you look at the anvil is right here, even though we don't have a flat and a rounded side, we know that we want that to go. Let's bring this down here. This way. So we want the short lead, the long lead to go on the rounded side, and the short lead to go on the flat side like that. And that's the proper way to mount that in there. Now, again, when you're using these in a current source, they are pretty consistent, because just like any other diode, they have pretty much a constant forward voltage drop. and they're kind of leveraging that to make your current source based on that, that voltage. But here's the thing, as these warm up, that just like any other semiconductor, that voltage drop will change slightly, but it's small. So once these get to kind of their operating temperature, they're pretty stable. But some people won't use those because of that. They'll use something else, a diode that has a better thermal track or something. But anyway, enough about that. These work really well. That's all I'm going to say. And anyway, if you don't have one with a flat side, and this is what I'm talking about when I say flat side. See how this side is flat, like this, and this side is rounded? I don't know if you can make that out in the video or not. It's hard for me to tell in the viewfinder if you can see that, but here's the flat side, here's the rounded side, and again, the long pin, which is your anode, and the short pin, which is your cathode. And it's a little harder to see in this one, but if you look inside there, you can see the anvil is still there. It has that shape, and the tail there, the anode side, if you notice, is still smaller, but it's a little bit bigger than the one we were looking at. But it's the same principle, same idea. Okay, all the diodes are in now, and if you notice the two Zener diodes, I left them a little bit proud of the board because these can get warm and I just want them to have better airflow. Same thing with these 56 ohm metal oxide or metal film resistors, whatever they were. I want them to be up off the board a little bit because these are what supply the voltage from the main supply, to the whole rest of this circuit here. So definitely want that to be correct. And I just noticed I got to tack these two ones in. I forgot. But the next thing we're going to work on is the capacitors. So I'll get those soldered right there, and then I'm going to start putting in the capacitors. Okay, a little note you might want to know. These 6 capacitors here, these are 150 microfarads at 100 volts. And there's 3 different options depending on what's available at the time, because availability of these sometimes can vary. The first one is these two right here are 150 microfarad and 150 volts, and they're radial. And if you use those, you can see you can use these ones or these ones. They're going to be like this. Okay, so these are 105. These are really good capacitors. And there's just basically 3 in parallel here and 3 in parallel here, and that's what gives you about 450 microfarads on each side. Now, if you want to use a axial leaded capacitor, you can see how they have this big rectangular outline, and there was a hole. You can see down here, there's a lead here and a lead here, a pad here and a pad here. See that? You can actually put a single 470 microfarad, 150 volt axial capacitor across there, and it'll fit in there. This actually gives you a lot lower ESR, and these are 105 degree capacitors, so this is a much better solution. But either one will work. But you just have to realize if you have one set, you don't need these other ones. Okay, the fun part, to put the transistors and heat sinks and all that stuff in. And what I'm going to do first is these small signal transistors. I'm going to put those in first because I don't want to have all these heat sinks in my way when I do it. And those are going to be, what are they calling those? These are KSA 1013s. KSC 2383. So that's what most of those are going to be. So let me dig those out. Oftentimes when you look at these, mass-produced receivers and equipment in general, you'll see the transistors all cockeyed, laying crooked on the board. And that's one one thing I don't like. I don't know, it's just a pet peeve. So what I do is I'll put the transistor in like this. I'll flip it over very carefully, hopefully it doesn't fall out. And I'll only tack in the center pin first. So just go ahead and do that. That just holds it. Then what I'll do is I'll go around and I'll make sure, kind of bore sight it, and make sure that it's perfectly straight up and down. And then I'll go ahead and trim the leads very carefully to their proper length. And yeah, this takes an extra minute to do this because you go back and forth, but when you're done, and then I'll go ahead and touch up the center one again. And when you're done, you have a perfectly mounted transistor. And that's, again, it's just one of those things. How many times you go in and you see a transistor, you know, it'll be mounted in there like this. And you start it, and it'll be all wonky like that off to the side. I can't stand that. So that's just a little tech tip there, that you can tack the center one in first, straighten it out, clip it, and then finish it off. So let me finish doing that and we'll be right back. Well, it's coming along, so I'll come back tomorrow and do a little more on it if I have time in the evening after work. But as you can see, this is kind of time consuming, especially if you want to do a neat job and double check everything, make sure you get everything correct. So take your time and do a good job. It's a hobby. Enjoy it. All right, well, I'm back on this today, and I got the heat sinks and the transistors mounted. And I just wanted to stop here to make a little note. This thermal fuse, when you install it in here, you just install it flush to the board, and then this is going to be sitting right on top of it in contact with it. And the idea is if this resistor ever overheats, which would happen in the event that this relay doesn't pull in, it'll overheat this thermal fuse, which will open. Now, as this is a thermal fuse, you don't want to hold your soldering iron on this for a really long time, or you could cause it to open up. So you want to get the iron on there, get the solder in, take it out real quick, and don't waste time, or you can trash it. So now I'm going to put this on there. And again, this is the soft start resistor. I'll probably mount it facing out so you can see the label there in case you ever have to replace it. And then the only part that will be left will be to put these terminal blocks, and we'll have to pull the heat shield off of the old board, which is easy enough to do, and you reuse that. That's the only part that is not brand new here, that is reused from the original board. All right, board number 1 is done. And I think it turned out really good. I can't wait to see how this all works. Well, this board's going to be a lot easier to do. There's not that many components on it, so I'll put this together real quick. I'll show you the finished product, and then that'll be the end of this part. And in the next part, what we'll end up doing is installing these into the amplifier. And we'll be getting really close to testing it out then. Well, sometimes the wheel is turning, but the hamster's dead. Fortunately, I keep my feathers numbered for just such an emergency. Good heavens. Now, is there any chance that this came out? Because, of course, this board's double-sided. I got a little... This is what happens when you're not paying attention. Okay, Let's do it the right way this time. Stupid. Well now. We will now return to our regularly scheduled program, already in progress. Well, there we are, ready to transplant these boards into here. And in the next part, I'm going to have to go through, and you can see all these terminals will have wires for them. And all those wires are at the bottom of these boards, and they'll each have to be removed one at a time, marked with their proper terminal number. And then we can remove the boards, and then we'll install the new ones and insert all the wires, and hopefully I won't get them switched around, but you know me. 50,000 people in the ballpark and a bird will crap on my head. So that's it for this part. And until, as always, I wish you all peace, joy, happiness, and good health in your lives, and we'll see you again real soon. Take care, everybody. Bye-bye.